Diana Valle. I am with the Electrical Engineering Department, and today we'll talk about our project, fiber optic sensing for wind turbine blades. Our agenda today includes abstract, introduction and background, project objectives, methodology, design specification, results, project delivered, project plan, project budget, project challenges, and conclusion. An accurate, cost-effective stress sensor system was designed in which the health of a wind turbine blade was monitored. This project examines the integrity of a blade during stressful environmental factors. Our system monitors temperature, excessive strain, and possible damages experienced by the blade. Fiber optic sensing provides a cost-effective solution to monitor the health of a wind turbine blade without physical contact, much use of bandwidth, minimal size and weight added to the blade, and freedom from EMI-induced noises. As the world steps away from fossil fuels, a need for alternative, reliable green energy has emerged. One of those markets is the wind energy market. Optical sensing can provide an accurate and noise-free strain measurement on a wind turbine blade without much added weight to its system. In the last 25 years, fiber optics has seen an immense growth and development throughout its applications. Fiber optics are very versatile, and its sensor applications can be used instead of traditional sensors in the fields of acoustic, vibration, magnetic measurements, and electricity, acceleration, rotation, high temperature, pressure, strain, humidity, and many other sensing applications. There are two types of fiber optic sensors. One of them is the extrinsic sensor. This sensor is less expensive and it's easier to use. They are usually used to measure temperature and liquid levels, and they can be placed in hard to reach places, which is a plus, and they are not as complex. The other type is intrinsic sensing. It works with direct modulation of light into the optical fiber head. Applications of an intrinsic fiber optic are strain, acoustic pressures, and vibration. It is more expensive than extrinsic and is more complex to use. For project objectives, we design a fiber optic pressure sensor. We perform analytical tests. We design a software to work with our system, and we executed a sensor response analysis between the sensor systems. Our methodology includes, we chose an intrinsic single mode fiber optic module because of its ideal uses. An intrinsic fiber sensing was a better option because its ability to test for strain, acceleration, and rotation, which are essential for our project. This is a schematic of our sensor, a single mode optical fiber head. Here we can see, we can have a better view of how our sensor will work. Light will come in. The applied force will combine with that and we'll get an output. This is a schematic of our software. Because you can't really see it, I will try my best to explain it. But overall, our sensor system has a validation process that checks for stress on the blade. It has boundary checks that allow the system to decide whether the blade is healthy or if the blade has been damaged. And it also has a trigger warning for possible damages. So we tested our prototype on a working wind turbine blade. Temperature sensors were applied in order to monitor the system temperature. Accuracy and stability of the system was recorded, and we also performed a fatigue test in order to check the accuracy of our output data and the overall health of the system. Here are some of the results we gathered from our fatigue testing. In blue, we can see our measurements, and in red, we have our reference numbers. We gather pretty good data from that. It is correlated. We also gather data, and this is load on a blade as a function of wind. We also compare our system with another system. In red, you can see our optical sensors readings, and in blue, an electrical sensor. As you can see, there's more red than blue. Therefore, our system checks more frequently for like a stress, or it can sense more. Our project deliberates. A pair of wind turbine blade sensor system has been completed. Final testing and optimizations were made to ensure the product provides an accurate stress sensing reading without overloading. The product we designed is ready for production after our testing, which are overall good. Here is our project plan. Overall, it took us 3 months to do all of this, and 2 months, about 2 months, were specifically used in order to test our prototypes and see whether we needed to make changes, whether the system needed to be more robust or not, and if there were any final specifications that needed to be added. The budget for our project includes the purchase of a E2000 fiber optic connector, a temperature sensor, strain sensor, and just miscellaneous items to put the whole thing together. Here's a better picture of what our budget was spent on. Most of our costs are for the E2000. Project challenges. One of the main challenges we encountered was finding a working wind turbine blade for testing of our system. This was a challenge because they're not just there. Another challenge that we had was fatiguing our system without causing any damage to the blade. In conclusion, our fiber optic sensing system is an innovation in today's wind energy market. The fiber optic system is cost effective yet complex enough in its ability for sensing. It can easily exceed the standards set by other sensors in the market today. Our sensor tests for stress on each blade and its overall health. The system validation system can check for in danger of failing blades. It also has a validation program within itself where if one sensor thinks the blade is having too much stress, it can check with a neighboring sensor to make sure that it's reading accurately. Overall, our system has performed well, and we are pleased with the results and the accuracy of our data. And we believe that we are pleased with our product, and we believe you will be pleased as well. Here are some of our references for our background research. And that's it. Thank you.